Hey everyone, due to some technical difficulties, this is a little later than I'd like, but this is chapter 13.4, which is spanning trees, and this will be the end of chapter 13. From here, after this, we'll go on to voting theory for the next chapter, but without further ado, here's spanning trees. So first we should probably talk about what a tree graph is. Uh, Basically, in the last section, we talked about connected graphs that had specific kinds of circuits. But some connected graphs don't actually have circuits, just at all. And we call those things tree graphs. So if you're curious of what a tree graph looks like, here are three different examples. And again, the only thing that we know about them is that they are connected and they don't have circuits. That's it. So you can't form any cycle, nothing, just just connected circuitless graphs. Now, the thing we're talking about, however, is spanning tree graphs, which is a specific kind of tree graph. But in order to talk about it, we're going to have to talk about a not tree graph. Just a regular graph that is connected, but not a tree graph. Okay, in this case, you can see that this is definitely not a tree because we have several cycles. You can see, for example, DEHD, that little triangle over there, that is a circuit which is against the rules. But we could redraw the exact same graph, but remove any edges that would have a circuit. So if you see here, this is one such example. Notice that it's still connected, and all of the edges in this new graph are from the old graph, but we just threw away a bunch of them. And this one definitely does not have any circuits, and therefore, well, it's a tree. And since this is a tree graph, we can call this a spanning tree graph. And the word spanning just implies that it uses every previous vertex from some original graph. But again, since it's a tree, no circuits. So we have this graph, and we can make a spanning tree from it, but the problem is that's not going to be unique, because there's actually more than one way to make a spanning tree, assuming that you had circuits to begin with. So which edge do you delete is kind of up to you. And instead, we want to find the best spanning tree. But in order to talk about what best means, we have to find a way of ranking them. And so to do that, we're going to have to add weights, just like from before. So I've added some weights, and in graph theory, once again, the lowest weight is usually the best. And so our goal is to find the lowest weight possible for a spanning tree graph. So find a spanning tree, find its weight by adding up all its values, and then finding out if it's the best by comparing it to all the other spanning trees kind of thing. One of the reasons we went over brute force for the Hamiltonian circuit problem is because there wasn't a best way. There were ways that we could approximate the answer and come up with what we thought might be good enough because they were faster, more reasonable algorithms. But there's actually a really easy algorithm to find the best one every time, and it's called Kruskal's algorithm. And Kruskal's algorithm is remarkably similar to the sorted edges algorithm, which allowed us to find an optimal Hamiltonian circuit. But that was only an approximation. It can still be wrong. This one, best time every time, which is very convenient. Step one, pick the cheapest edge. Again, find the one with the lowest possible value. Step two, repeat step one, unless the new edge creates a circuit. And then step three is just keep doing all of this over and over and over and over and over again until you have a spanning tree. And that's it. The algorithm is almost uh, a... So let's actually apply Kruskal's algorithm. Well, we're going to have to start with a connected graph with weights, and it has to have some circuits, otherwise we're going to just be done already. So here's our connected graph. It's got some circuits, and we're just going to remake the exact same graph, but it's just going to not have edges. And there we go. And then we're going to pick the cheapest edge as long as it doesn't make a circuit. That's the entire algorithm. Keep doing that. So we've got DH. Because 7 is the absolute smallest number on the list, we're going to start with that. And there we go. No circuits. CH, well, that's right next door, but that's okay. That's still not a circuit. It's just a slightly longer path, which is fine. Followed by DE, that's a 12. So that's 12. Followed by AC, which is 14. Followed by FG, because 19 is the next smallest in the graph. But you'll notice that it's not connected, and that's okay, because this algorithm doesn't require that, because in the end it will connect, don't worry. So with that in mind, we then add GI, which adds a little bit more to the FG edge, and HI, which connects everything as I said it would. And that's 42. And those are just the cheapest things in order, and there hasn't been a problem so far. You can notice that this is in fact a tree, except there's that B that would make it disconnected. But that's okay, because our next thing to look at is CF. Well, actually CF doesn't work because, well, if you see CF over here, well, that CF, that would make a circuit. We'd have a little circuit that goes around starting at C, going to H, then I, then G, then F, and then back to C again. And that would be inappropriate. We can't have that. So, well, let's go to the second cheapest. And that happens to be 73. And you can check, but it's I made sure it is 73. And so, well, that's a spanning tree. We're done. And now we know the actual value. We can just add all those values up, and I get 183. This means that this is a optimal spanning tree, and more importantly, we also know its value, which is 183, which can be pretty useful. Now this seems a little bit weird, because why would you need to do this in real life? Well, one of the most common applications has to do with network capability, so let's give an example. So we'll say that Larry, he has to connect all the computers in the office with networking cable, and he wants to make sure all the computers are linked to each other, so he wants to be able to them to directly communicate, and they don't have Wi-Fi. So he doesn't want to waste cable just connecting machines that are already connected. So he can talk about all of the possible cable lengths, like he knows how far the cable would have to stretch in any particular case, but he doesn't want to draw all of them, because then he'd have to buy a bunch of cable and hook it up, and he don't want to do that. So his question is, what's the absolute minimum amount of cable to make it so that all the computers are connected in some form? That's it. This is a real problem. If you have a hard time seeing how this would be a real problem, another problem would be laying power cables, where, again, I don't want to repeat sections if I can connect to it from somewhere else, or talking about water lines or sewage lines or anything like that. Oftentimes this is a thing that we'll talk about in infrastructure stuff. But let's try to solve this problem. So we're going to have our fun graph, and we need to use Kruskal's algorithm because, well, that's the algorithm we have. The cheapest edge in this case is going to be 2. So we're going to add it to our new graph. You can see there's a 2 near the top. It's the cheapest one. Then, well, the next cheapest, that's a 4. Right? So far, so good. Now, the next cheapest is a 5. You can see 2, 4, and then there's a 5 at CD. But if I connect C and D, I'm going to get a triangle, and a triangle is a circuit, and I'm not allowed to have circuits, so we can't pick CD. So instead, we're going on to BE, and BE is 6. And so we get that 6 there. And then the next ones are, again, we're just going to pick the cheapest, and there doesn't seem to be a problem. We're not going to make another cycle. So this adds, and by the way, this will connect all the vertices. DE or ED both work, and that is a score of 12. So, total length of cable to solve this is 2 plus 4 plus 6 plus 12, which is 24 feet of cable. And again, the thing that you're trying to avoid is, for example, you don't want to connect A and B if I already have a route from A and B, right? This is super fast cable, who cares if there's two computers in between? And that's kind of the idea. That's why we would solve this problem. And that's kind of the whole point. So, with this in mind, that's basically it. Now, in the previous sections, I didn't actually have like a little final thoughts section, but this is the end of all of the notes for chapter 13. So if you do have questions about this chapter or anything else in this course, please contact me. I always say that, but it's always true. I do mean it. I will try to get back to you as soon as possible. If I don't respond within 24 hours, it is a pretty good sign that I somehow missed your email, and please email me again. I will be very happy to help any kind of requests. As I always say, it is literally my job. And so, the homework and quiz, they're going to be due this Sunday, right at midnight. That's April 4th, for those who don't know when that is. And you're going to have 24 hours after that to work on the test. My office hours are on Monday, Wednesday, Friday from 12 to 1 or by appointment. And again, by appointment just means you send me an email and say, hey, I don't understand, chapter 13, or I don't understand, this section or this homework problem. Can I come to your office hours at a different time? And then you tell me what time works for you, and I will do my best to support it. My schedule's pretty flexible, so I will be happy to help in any way I can, I promise. And with that, I'm out of stuff. So all I have to say is, have a great day.